Okay, let's continue for our discussion from Tuesday. In Tuesday, we introduced the idea of gradient operator, which is a spatial differentiation operation on scalar. Unlike the curl operator and the divergence operator, which are performed on vectors. The gradient operator is a spatial derivative performed on scalar, which are pure quantities, which are not vectors. So in this slide, it shows essentially the gradient operator and its operation and its physical significance. So from this equation, we know the phi, which is the change in phi per meter equals to del phi, that is the gradient of phi, times dl, a differential length, a short distance, a short piece of distance. And as you can see here, they are combined in terms of dot product, dot product. So the operation, the dot product operation is operated with two vectors. So even though that phi itself is a scalar function, 存量的函数, phi 本身是存量的函数, but once you take the gradient of phi, it becomes a vector. So, and the differential length dl is also a vector. So the dot product of the two vectors end up with the phi, which is a scalar or a vector. It becomes a scalar, all right? The dot product ends up with a scalar. What is the significance of d phi? It says the difference in phi, the amount of difference in phi. So you can interpret them as 变化量，所以 d phi 的话可以称之为变化量。那梯度呢是变化率这一个物理量的变化率。dl 呢，我们讲的 differential length 呢是一个指定的方向。所以用这个 operator 打下去，操作之后呢，你可以就是说，这一个物理量 phi 呢，沿着特定方向走一小段之后，它所得到的变化量，而那个 del phi 那个 gradient 的 phi 呢，是在那个位置观察位置附近的这个物理量 phi 的变化率。So we also know that gradient of phi is a vector. So as you can see, it expressed in terms of del phi over del x, del phi over del y, del phi over x, and it's distributed in the x, y, and z direction. That's the gradient operator in the Cartesian coordinate system. 直角坐标的梯度的表示式啦，5.7。We also know that divergence is performed on vector and you end up with a scalar, and curl operation is performed on vector as well, and it ends up with a vector. And gradient is performed on scalar and you produce a vector. And the gradient operator in the Cartesian coordinate system is relatively straightforward. You're just taking the partial differential equation toward x and y and z, and the product is placed in the x, y, and z direction. On the other hand, for gradient operator in cylindrical and spherical coordinators, the expression is a little bit complicated. As you can see, I marked the extra parameter that is required in the gradient operation in cylindrical and spherical operation or coordinate system. Why? Because in cylindrical and spherical coordinate system, the axis phi and axis theta phi, they are quantities of degrees. They don't have distance. they don't have distance. So in order to incorporate them with the so-called differential lengths, you need to keep the quantities theta and phi need to be coupled with r, the distance from the z-axis and the distance from the origin for a spherical coordinate system, so that you can have, you need to have, say, like r d phi or r d theta and r sine theta d phi, so that you have the change in distance in the theta direction, in the phi direction. Okay? Right, so the consequence of this coupling ends up with some extra parameter in the operation, in the gradient operation in the cylindrical and spherical coordinate system. So you need to be aware of that. And I don't know about that because if you are asked to perform gradient operation in cylindrical and spherical coordinate system, I will provide the equation in the cheat sheet of the exam 所以考试时候大抄上面会有这一个用著作标系统跟求作标系统的那个梯度的操作纸我会放在那边，所以倒不用去背它了但是你要知道有这回事 ，OK 那在做 homework 的时候记得跟他搞熟悉一点，好不好？To discuss the physical interpretation of the gradient, let's consider a surface on which phi, the quantity phi, the function phi, is equal to a constant, say phi sub 0, and a point P on the surface as shown in the figure to the left. So on this surface, we have a point P, and the interesting thing here is on this surface, the quantity phi is the same everywhere, which is similar to the so-called plane wave. When we do the derivation of plane wave in chapter 3, it describes that a plane wave can be generated with an infinitely large current source, so that the electric and magnetic field are the same everywhere on this specific plane. So the quantity phi is the same on this plane. So if you move from P to Q1, or move from P to Q2 or Q3, how about the change in phi on this path? Well, the amount of change is 0. The moment change of 0 on the same plane. On the other hand, if you're moving from point P on the surface to the back to a point Q that is on the surface in front of it, you may experience some differences in phi. If on the back the phi is phi sub 0 and in the front is phi sub 0 plus the phi, then the amount of change in phi is what? It's d phi. Okay? So that's two constant for the figure to the right it shows two constant plane of different quantity of phi. Alright? So record that the definition of gradient operation, we know that the dot product of the gradient, say del phi times differential length, dl, equals to what? The amount of change in phi. So if we do the test on several differential lengths on the plane, then as I already mentioned that starting from point P, the gradient of P dot dl equals to 0 because there's no difference in phi on this path, and it has no difference on the other path dl2, dl3. And what is the significance of this? What is the significance of this equation? Now, if the dot product of the two equals to 0, because it's the dot product, 内积嘛, so it says you can interpret it as the two vectors, del phi at P and del1 are what? Perpendicular to each other, or orthogonal to each other, 互相垂直, orthogonal 啊，交叉 orthogonal 或者 perpendicular 都可以，或者说它们是正交，perpendicular. So that the gradient of phi at point P and a small and a differential length starting from point P equals to 0. This is true for DL1 and it's also true for DL2, DL3. So what is the consequence of this result? The gradient of phi at point P is perpendicular to any vectors located on the surface. 也就是这边所写的嘛。这一个点注意哦。Gradient of phi 在不同的位置是不一样的所以这个小 p 指的是在 p 这一点的梯度phi 这个参数的梯度。当然了，假如我们看的是刚刚的那个平面波那其实其他点的那个梯度也是一样的因为它们是平面波都是一致的但是只要是任意的函数变化的话，不同位置的那个梯度不一定相同所以结果是什么？结果是 P 点在 P 这个点的梯度 del phi 跟平面上的任意一个线段是垂直的，所以你可以用这个方式找出它的第一个你的 conclusion 是什么？第一个 conclusion 是 del phi at P is normal to the surface， 跟这一个平面是垂直的，也就是说，它的方向跟这个平面的法向量 P 所在的这个平面的法向量是同一个方向的So the significance of this result is that the gradient of phi at point P is pointing toward the normal direction of the surface of this planar surface. So the gradient vector is the same as the normal vector of the surface. Suppose that you have a surface wave or you have a plane with a consistent quantity, then the direction of the gradient is the same as the normal direction of the plane. And what if we do the dot product along direction that is pointing out of the surface? For example, if you starting from P to Q, which is located on another plane that is a little bit in front of the plane and behind, then what is the dot product of del phi and dl, this short distance? Well, it should provide you the difference of Q, or the difference of phi in the two planes. We know that the dot product of gradient of phi and differential length shall produce the difference of the function phi. And in this case, the selection of the point Q can be an arbitrary point. It doesn't have to be in front of P. So as you can see here, the vector PQ, the vector connecting from point P to Q, has an angle with the normal direction on P. Then the angle is alpha. And according to the definition of dot product, you have what? If you do the dot product of gradient of phi at P with dl, you end up with dl cosine alpha. So it's just the projection. You can interpret it as the projection of the distance dl on the normal direction, right? 也就是说，这个告诉什么 ？dl cosine alpha 告诉你什么？它代表的是 PQ 这一个线段 dl PQ 这个小线段在法线方向 AN 上面的投影量，所以它只取出有效的部分，也就是跟它的，因为我们知道什么 gradient of phi 呢是在法线方向，那 dl 呢是一个没有跟 gradient of phi 正交的向量，所以既然它不正交，那它们的内积就不会等于0。那它们内积的意义是什么？它们内积意义是找出它在梯度方向上面的投影量，所以而这一个量，the product of the result of the dot product is what? Is the amount of change in terms of in phi at the two planar surfaces, alright? So you can rewrite the expression. You can rewrite this equation like this. So gradient of phi at p equals to amount of change in function phi over dl cosine alpha. So no matter you can place q at an arbitrary position, but the amount of change d phi is the same for two observation points on the planar surfaces, on the planar wave. So dl cosine alpha, which is the projection of dl on the normal direction of the surface, is the shorter distance. Is in fact the shorter distance between the two planar surfaces. So you can interpret it as del phi at p is the maximum rate of increase of phi at point p. 所以，好吧，所以这边的文字请你再多看几次吧，中文、英文都好，多念几次吧，所以梯度向量是什么？梯度向量是任意点，在你所观察的这个物理存量在那个点的最大变化率的方向那下面图我们之前有礼拜二的时候稍微提到过嘛假设它是一个高度分布好了那黑色是高度比较大的地方还是比较小的？它高度是比较大的啦，因为根据我的蓝色箭头，也就是梯度，注意梯度是向量，所以它有大小也有方向，它有大小也有方向。那个箭头长短，通常箭头长短代表的是梯度的大小嘛，那箭头的方向那就是那个梯度的方向，所以左边的图你可以看到中间的那个黑色区域是山峰，山峰。那右边的图的话，它是一个山坡啦，左边高，右边低，那注意蓝色箭头代表什么？代表它的是这一个物理量 phi 由低到高的方向，注意一下gradient of phi 它是由数值小的地方指向数值大的地方，这是数学上面的操作定义，但我们今天等一下会讲到，在你在讨论所谓的电场跟电位或者电场跟电压的时候呢，我们当初200年前在对电场方向做定义的时候，不小心弄得不是很合适，所以我们在发现电场跟电压的关系是有多一个负号，因为我们在电路学里头，你是怎么定义电压跟电场？你是那个电场方向是高电位指向低电位，是吧？对，那刚好跟梯度的那个定义是倒过来的，所以你在那个我们在写电场跟电压的关系的时候，其实写作什么？等一下我会再看到了 ，E 等于什么？负的 gradient of V 电压的梯度的负值是你的电场方向我们等一下会再讲到。But Okay, so the gradient of a scalar function phi at a point is a vector having magnitude equals to the maximum rate of increase of phi is a point and is directly along the direction of the maximum rate of change. So now that gradient of phi is a vector, its magnitude is the maximum rate of change, and its direction is the direction of maximum rate of change, which can be derived with this definition. That is, the amount of change. The phi is the amount of change. The n is the direction of maximum change. Maximum change. So the phi over the n is the maximum change, and an represents the direction of maximum rate of change. So the gradient of a scalar function can be used to find a unit vector normal to a given surface, as shown in the next case. So here is an example. So let's find the unit vector normal to the surface y equals to x to the square at the point 2, 4, 1 by using the concept of the gradient of a scalar. Okay, so now, what kind of a surface is this? Y equals to x to the square. Well, it refers to a hyperbolic surface, right? 抛物面嘛 ，y 等于 x 平方是抛物面。那注意它后面的那个观察的那个坐标点是2、4、1，所以它是什么？它其实是在三维空间的，也是 x、y、z 嘛。好，那你看那个曲面的描述式里头有没有 z 的描述？没有所以它其实是一个 xy 平面上面的 y 等于日轴在哪边？日轴在这个方向出来的x 记得用右手x y z， 所以 y 等于 x 平方，所以它长什么样子？y 加等于4的话 ，x a 的话正负2嘛，OK。所以它是一个 y 等于 x 平方的抛物线，然后呢，它会沿着 z 轴无限延伸，所以它其实是有点像你拿一张 A4 纸把它折起来这样子 ，OK， So we have an equation representing the surface which can be defined as x to the square minus y equals to 0. So that's your function. And now that this is a scalar function because you don't have ax, ay, and az. You don't have projection on the x, y, z direction. So the function itself is relatively simple, just x to the square minus y. And what is the gradient of this? Well, it's not that difficult. It's just taking the partial differentiation in the Cartesian coordinate system like this. You're taking the partial difference in the x components, y component, and z component respectively, and the product is 2x ax minus ay. So now that here you have a vector. And also now that this vector is a dependent of position. 有没有注意到？你的做了梯度的操作之后，你得到一个向量，而这个向量本身呢，并不是一个常数哦，它会跟什么？会跟你的观测位置有关。它是2x ax 减 ay 所以它跟 x 的坐标有关。所以 if you want to look at the gradient of phi at a position 2, 4, 1, what is the gradient at a position 2, 4, 1? You substitute x equal 2 into this result. You end up with what? 4ax minus ay. So that will be the gradient. The gradient of the surface y equals to x to the square at the position 2, 4, 1. So this figure shows the phi function which is drawn in the red line And you also know that it's expanded infinitely toward a positive z and minus z direction. And your observation point is the black dot over here. And in fact, the gradient direction has two directions. One is pointing to this way and the other pointing to its opposite direction. So if you even know that the vector 4ax minus ay is one vector, if you take in the unit vector of it, it becomes this, right? This becomes minus and positive and minus. So that are the normal direction of at that point 2, 4, 1 on this hyperbolic surfaces. Hyperbolic surface. It can be pointing toward the 2 direction, right? Another thing that 我们今天提醒一下在我们电磁学里头，假如你有一个几何结构，一个面是有边界的，那么请问面的方向是哪样？假如说这是一个平面好了，那中间那个点的面的方向，法线方向有是哪一个方向？这边跟这边都是，它都是合法的，你有前面跟后面，所以假如你的面不是一个封闭面，是一个有边界的面的话，那它的面的法线任意点的面法线方向其实有2个，前面跟后面嘛 ，OK 但假如说你的 geometry 是一个封闭面，比如说这个 bottle 的 surface， 什么叫封闭面？假如你能够把坐标系统的原点包在里面的话，那它就是一个封闭面嘛。事实上它是你不能说找不到它的边界。所以假如是这样子的封闭面的话，那它的面法线方向对于任意点的面法线方向只有一个朝外。朝外就好，就抓朝外就是了。OK， 跟大家提醒一下。但像这个的话，因为它不是封闭面嘛，所以它的法线方向有正负2个成分。OK， so you can using the gradient operation to help you find the normal direction on that surface. And then we will move on to our next topic. We will try to I will try to show you the use of potential because on Tuesday we introduced the idea of electrical scalar potential and the magnetic vector potential. Electrical scalar potential phi and magnetic vector potential A. Magnetic vector potential, electrical scalar potential. And how does this equation come from? This equation comes from Faraday's law. Says that the curl of E equals to the minus of time derivative of B. And 我推一下吧 curl of E. And we also, in fact, we begin with divergence of B. 磁动量密度的散度 equals to 0, so that we can use vector identity to claim that B can be expressed as the curl of vector A, and A is the so-called magnetic vector potential. So if we substitute this representation that replace B with curl of A, we end up with what? We end up with this thing. We end up with this equation. And we also know that The equation above is the curl of a vector, and it equals to 0. Because it equals to 0, we can take advantage of another vector identity, that is the gradient of a scalar becomes a vector. If you're taking the gradient first, then taking the curl of the scalar, it becomes zeros for all times, for all scalar. So we can define the thing in the small parentheses as the gradient of a scalar. So we have this expression that the electrical field intensity can be represented as minus of a gradient of phi minus the time derivative of A, so that the electrical field intensity E is related to spatial derivative of electrical scalar potential and time derivative of magnetic vector potential. 好，这边听清楚啊。所以电场这个式子的物理意义是什么？电场它有2种来源，一个是持向量位能的时间变化，就后面那一项，而另外一个呢，则是电存量位能的空间分布的不均匀。啊，所以注意到这后面2个跟的都是微分。第一个 del 波的告诉你的什么？空间上面的不一致，空间上面的不均匀。后面那个告诉你的什么？时间的变动，在时域上面的变动。啊，所以持向量位能的时间变化跟电存量位能的空间变化都是电场的来源。OK， 好。So in the derivation of this relationship, we use what? We use first the first Maxwell equation and the fourth Maxwell equation. So we have another 2 Maxwell equations left untouched. So what? So I'm trying to well, before we push further, so let's wrap up a little bit about the relationship between magnetic vector potential A and the electrical scalar potential. So in this slide, it says that the magnetic vector potential A is directly related to source current density J. We also know that J, the electrical current density, is the fundamental source of magnetic field. And the charge density rho is the direct source of electrical field. And the electrical scalar potential is directly related to charge distribution. 所以这边再复习一下了哈。在我们的电磁场、电磁波里头有2个能量的来源。电场跟磁场是能量，电场跟磁场是能量，而这2个电场跟磁场的直接来源是电流跟电荷。电流是磁场的直接来源，电荷是电场的直接来源。所以从直觉上来讲的话，磁向量位能应该要跟电流有关，就是那个 A 跟 J 必须要有关系，而电存量位能 phi 它跟谁要有关系？跟电荷密度 ρ 应该有关系。所以这边先跟你讲一下，提示一下，因为我们等一下要做的推导跟这件事情是有关系的。So for we already see this equation. It says that the generation of electrical field is related to spatial inhomogeneity of phi and time variation in A. What happened with static field condition? What happened with 进场？只要在进场条件的时候会变成什么事情？在进场条件的时候没有 time dependence 嘛？So for static field, the second term vanishes. So second term vanishes. It becomes what? It becomes this. 我们在电路学里都看到的。 的梯度的负值等于电场。And we also know that, well, even though that we say that the source of magnetic field is electrical current, and the source of electrical field is charge, what difference between charge and electrical current? Well, I suppose you already know that electrical current is formed with moving charges. However, in the study of electrical magnetics, the charge and the current can be treated separately. No, you don't know that. But we also know that the relationship between Rho and J, the charge and the current, which can be related in terms of the so-called continuity equation. That is, the divergence of J equals to the minus of the time derivative of Rho. So for a specific point, if we have some current Rho, and the quantity of Rho becomes smaller and smaller, which means it's losing electrical charge to somewhere else, then the associated physical phenomenon is what? Is the outgoing electrical current, right? So the continuity equation is not that difficult to understand, right? So using this equation, you can relate electrical charge and the electrical current. And now let's move on to the other two Maxwell equations. So if we look at the Ampere's sequential law, that is the curl of H equals to J plus time derivative of D, the electrical flux density. Then in the static field case, that is the time derivative equals to 0, then you can see that H is directly related to J, and E is directly related to Rho. So under the condition of a steady field, electrical scalar potential and magnetic vector potential are independent. They are not related to each other. On the other hand, for time variant cases, for non-statistic conditions, the electrical scalar potential and the magnetic vector potential are interdependent. They are coupled. They cannot be treated as separate quantities for time variant cases. So to proceed further, let's record the Maxwell equation in differential form like this. So as I already mentioned, the direct source for electrical field is electrical charge. The direct source for magnetic field is current. And the time variant behavior, the time variant electrical field and the time variant magnetic field will continues to produce electromagnetic wave, as we already seen it in chapter 3, where in chapter 3 we already show the derivation of electromagnetic wave in terms of the coupling between the first two Maxwell equations, in terms of because of the time difference in magnetic and electrical field. Alright, so let's continue for our derivation. So at the beginning we're starting from Gauss's law of magnetic field. So we see that B can be expressed as the curl of magnetic vector potential A. And using the Faraday's law, we end up with E equals to minus of a gradient of phi minus the time derivative of A, so that we can show electrical field intensity in terms of spatial derivative of phi and time derivative of A. Now, let's try to apply this relationship to the two remaining Maxwell equation. Let's begin with Gauss's law of electrical field. Okay, so it says the divergence of D, which is also the divergence of electrical field intensity, E equals to rho. So we can rewrite that equation as divergence of E equals to rho over epsilon. Now, what is epsilon? Permittivity. 介电系数。epsilon 是介电系数 ，mu 呢介质系数。OK， 等一下会看到epsilon 跟 mu 出现了哈。And so in this equation, we replace E with minus of gradient of phi minus time derivative of A like this. Okay? Then we also substitute this relationship, the two relationship above into the Ampere's Kirchhoff law. So H is replaced with curl of A. Well, in fact, H equals to what? H equals to B over mu equals to curl of A over mu. Right? So you can replace curl of A over mu here. So you place mu to the other side, right? And the second term is originated from what? Comes from the second term on the right-hand side, that is the time derivative of D. So with some manipulation, 这边你要自己做一下哦，好不好？回去这边自己要看一下哈。这边式子其实没有很难啦，哈，你就照着前面的几个关系式，把这边的式子自己推一下，这样你才会有印象，好不好？实际上就是只把这一项摆到前面，然后除以mu乘上mu还是除以mu？whatever 自己试了 ，OK 好。反正出来一个 mu option 在这边了，OK。这个就是那个电场 E 嘛，对不对？这是时间微分嘛，这边时间微分。然后那个 J 呢留在右边等号的右边但因为我们都有乘一个 mu 嘛所以 it becomes mu times J for the second equation. Alright, now we have two equations. The two equations. It looks a little bit messy. So what is the significance of this two equations? What is the importance of the two equations? Well, we need to, before we proceed for the two equations, we need to pause a little bit and introduce another mathematical tool. That is the Laplacian, right? Laplacian. What is the significance of Laplacian? Well, Laplacian is a second-order spatial derivative. Laplacian operator is a second-order spatial derivative. Laplacian operator 是什么？它是空间的二次偏微分，它是一个二次空间偏微分的操作子，称之为 Laplacian。当然，等一下我们会跟你讲 Laplacian 长什么样子，偷看一下长这个样子。那拉普拉线比较讨厌的是，它有分存量的拉普拉线，还有分向量的拉普拉线。那直角坐标系统里头的拉普拉线操作还算单纯。当圆坐标、球坐标系统跟柱坐标系统里头的拉普拉线就比较复杂，特别是向量的拉普拉线会看起来有点可怕。不用怕，那个式子我都放在考试的时候都放在大抄里头的，OK。应该说这一类的操作是一定会考的啦，你想想看，你把它熟悉一下，你的那个期中考就15分到20分入袋了所以要记得练习写作业的时候那个归链拉普拉线还有克跟 divergence 的操作都要熟悉，好不好？Right, so the thing in the red box is the definition of Laplacian of a scalar. So it writes up as del square phi. That is the Laplacian of the function phi. Equals to what? Equals to the 这怎么念？学起来哈 ，divergence of the gradient of phi 所以把 phi 先取梯度，再取散度它就相当于我们这边所定义的存量的 Laplacian The divergence 念的时候从外面往里头念嘛The divergence of the gradient of phi of the function phi. And we already know the representation for gradient of phi is this in the Cartesian coordinate system. And the dot product is this. So if you do that, you're taking the operation further, you're taking the Laplacian of phi, which is combine the two equations over here. It looks like this. It's relatively simple in this case. It's like just simply taking the second order derivative of phi toward x, second order derivative of phi toward y, and second order derivative of phi toward z. And it ends up with a scalar or a vector. It's a scalar, right? Because in the red box, you see that Laplacian of a scalar is the dot product of two vectors. So you end up with a scalar. So the Laplacian of a scalar is a scalar. So here you have a scalar. And because x, y, z are decoupled in the Cartesian coordinate system, so the expression for the Laplacian of phi in the Cartesian coordinate system is relatively simple. Just taking the second order differentiation toward x and y and z direction in the Cartesian coordinate system. And in this slides, because r phi z, well, r and phi are decoupled in the cylindrical coordinate system. R and phi are decoupled with z 所以在柱状调系统里头 r 跟 phi 是绑在一起的，但 z 跟他们两个无关所以你会看到在 5.20a 也就是柱状调系统里头的 Laplacian operator 长起来有点前面两项比较复杂一点那个 r 有的在里面，有的在外面So remember, you need to perform the derivative of phi toward the r direction first, then times r, then taking the derivative again toward the r direction 所以在操作的时候要注意顺序在顺序，你不可以一口气把这个 r 说要跟外面的消掉不可以这样子那个顺序要保留住但是像第二项的话，那个 r 平方分之一就直接摆在外面了 ，OK？ 那么下面是那个球状调系统的存量Laplacian那你会看到，因为 r、西塔、phi 三个都 couple 在一起所以那个表示是比较繁琐一点但就像我上学期讲的电磁学里头的数学不难，它只是比较烦比较麻烦一点但它其实那个操作都相对算是单纯的 Okay? So here we introduce the idea of Laplacian of a scalar, right? So here are some things that you should review. The curl of a vector is a vector, the divergence of a vector is a scalar, the gradient of a scalar is a vector, and the Laplacian of a scalar is a scalar. The Laplacian of a vector is also a vector. Let's see. So let me finish this part. The Laplacian of a vector. So by definition, 不好意思，定义比较复杂一点To the top right is the definition of the Laplacian of a vector. It's expressed as the gradient of divergence of A minus the curl of A. So it's a little bit complicated. Fortunately, if you try to express the Laplacian of a vector in the Cartesian coordinate system, you can simply reduce to 3 scalar Laplacian of Ax, that is the projection of vector A on the x direction. The Laplacian of a scalar Ax, the Laplacian of the scalar Ay, and the Laplacian of scalar Az. And as you can see, the Laplacian of a vector is a vector. Now you have Ax term, Ay term, and the Az term. And because the Laplacian of because the Cartesian coordinate in the Cartesian coordinate system x, y, z are decoupled, so the Laplacian of the vector is relatively simple. And in the textbook, you should find the Laplacian vector Laplacian, the vector's Laplacian operation in cylindrical and spherical coordinate system, which is somewhat scary. All right, let's rest for 10 minutes. 我们先休息一下。